Hi all, welcome to the lecture series on Aerospace Propulsion. Myself, Mr. Manideep Gupta, Assistant Professor from Department of Aeronautical Engineering, MLR Institute of Technology. Coming to the today's topic, today we are going to discuss about liquid propellant rockets, which is a very essential part of propulsion system. Coming to the overview of today's presentation, today we are going to discuss about the introduction to liquid propellant rockets, what is liquid propellant rocket and what are the major components in the liquid propulsion system. We'll discuss about the propellant feeding system. This is a major important component of a liquid propellant propulsion system. In that, gas pressure feed system is one of the type of propellant feed system. And next, liquid propellant properties and liquid oxidizers, fuels. So these are the topics which we are going to cover in today's presentation. Coming to the first, introduction to the liquid propellant rocket. What is liquid propellant rocket and how it look like? See, this is how a liquid propellant rocket look like. Here, the first one is this 1 and 2 are the fuel and oxidizer tanks, and this is the pumping mechanism. And the fourth one, this is the combustion chamber. Fifth one is the nozzle, and sixth is the exhaust. Okay. The main parts of the rocket, liquid propellant rocket. One is payload, liquid rocket fuel. Here, this is liquid rocket fuel. Next, oxidizer. Okay, fuel and oxidizer. One is fuel and two is, this is fuel, and we can consider oxidizer generally we indicate with a blue color symbol. Okay, and pumps to carry the fuel and oxidizer to send this propellant. Okay, whatever the propellant stored is in this tank, it has to send to the combustion chamber. This is the combustion chamber. Okay, it has to send to the combustion chamber with the help of pumping system. Okay, the combustion chamber, nozzle and exhaust. These are the major components of liquid propellant rocket. What are the advantages of liquid propellant rocket? Coming to the advantages of liquid propellant rocket, the specific impulse is high. The specific impulse is high, and we can produce large amount of thrust in liquid propellant rockets when compared to the electric thrusters, electromagnetic thrusters and electrostatic thrusters. So the thrust produced by the engine also high. And next, high thrust to weight ratio for liquid propellant rockets. The thrust to weight ratio is also good for the liquid propellant rockets and easy to control. With the help of this liquid propulsion system, we can control the direction of the vehicle easily, and also we can control the thrust level. Okay, we can easily control the burning in liquid propellant rockets. Okay, and next, effective propellant utilization. We can use the complete fuel. Okay, the fuel will not go wasted. Okay, we can use the propellant in effective manner in liquid propulsion system. Whenever we require, we can increase the propellant mass flow rate. Whenever we require, we can decrease the propellant mass flow rate according to the requirements. We can control and we can easily maintain the propellant flow so that the effective propellant utilization will be there in the liquid propellant rockets. And next, coming to the enhanced reliability and life. The reliability, reliability of the liquid propellant rockets is more when compared to the other propulsion system, and the life of the propulsion system, this liquid propellant rockets, is also high compared to other propulsion system. And it also provide for reusability. We can reuse these liquid propulsion systems in some cases. So these are all the advantages coming to the liquid propellant rocket. Next, disadvantages. Even there are some disadvantages. The thing is, the design is complex. Okay, we have to consider so many parameters while designing a liquid propellant rocket. Okay, the thrust chamber will be there. Okay, the main thing, the complexity involves in, we have to store the propellant in separate tanks. Okay, after that, we have to pump the propellant from tanks to the thrust chamber with the help of pumping system. So we have to design a good pumping system. Okay, and after that propellant has to be injected in the thrust chamber in an effective manner. Then only the combustion happens in a efficient way. So all these complexities involves in designing liquid propulsion rocket system. So the complexity is more when compared to the solid propulsion system in the liquid, and it is impossible to achieve very high specific impulse. Okay, we can produce high specific impulse in the liquid rockets, but we cannot produce very high specific impulse compared to the solid propellant rockets. Okay, compared to solid propellant rockets, the specific impulse in liquid propellant is less only. As the thrust generation increases, as our requirement of increasing the thrust increases, the complexity of the design also increases. So complexity grows quickly with growing the thrust. As we want to increase the thrust, the complexity of engine increases. This is one of the major disadvantage. Because of that, we cannot generate high specific impulse in the liquid propulsion system. And some propellants are toxic. Okay, some liquid propellants are toxic, and even you can see cryogenic hydrogen. Okay, hydrogen way and monomethyl hydrogen, UDMH, MMH. So there will be some toxicity in liquid propellants. So this is also one of the disadvantages in liquid propulsion system. Coming to the next topic, liquid propellant feed system. So it is a very major component in liquid propulsion rockets. Okay. So liquid propulsion feed system. What is the main aim of this propellant feed system? This propellant feed system helps in pumping of the propellant from the tanks to the thrust chamber according to the requirements for better operation of CC. CC means combustion chamber here. The CC means combustion chamber. So the main aim of this propellant feed system is it has to pump. Okay, the main aim of propellant system is pumping of propellants from where? From tanks to the thrust chamber, that is combustion chamber. Just pumping is not enough. It has to control. We have to control the flow of propellants, and also we have to provide the propellants to the combustion chamber at required pressure and temperature. Okay, so if you do not provide the propellant at a required pressure and temperature, the combustion process in the chamber will affect. It will not be efficient. So the combustion efficiency or the combustion process is completely dependent on the propellant feeding system. So it is a very important component of liquid propulsion system. Okay. Coming to the functions, what are the main functions? Okay, coming to the functions of the propellant feed system, the thing is rising the pressure of the propellant according to the requirement. Okay, so we have to inject the propellant at a particular pressure in the combustion chamber for continuous combustion. Then only the process will be continuous. Otherwise, if you do not maintain a proper pressure while injecting into the combustion chamber, the process will affect. That's why propellant feed system will help raising the pressure of the propellant and also feeding the propellant to the thrust chamber. Okay, with a feeding with a required mass flow rate, and also the pumping system itself maintains the proportion of fuel and oxidizer which we are sending into the combustion chamber. Even the ratio of liquid oxygen to oxidizer to the fuel ratio also will be maintained by the pumping system. Okay, coming to the types of feed system. Coming to the liquid propellant feed system, there are two major types of propellant feed system. Okay, one is pressure feed system and the second one is pump feed system. Okay, pressure feed system means here we maintain some pressure in the propellant tank so that the propellant will be automatically supplied with some pressure required to the combustion chamber. Coming to the pumping feed system, we use the help of turbo pumps. We use the help of turbo pumps, we supply water from one place to another place with the help of motors, right? The same way we use turbo pumps for pumping of the propellant from tanks to the thrust chamber according to the required pressure. So these are the two methods of a propellant feed system. One is a pressure feed system, another is a pump feed system. Okay. Coming to the here, you can see the diagrams here. Coming to the gas pressure feed system, there are two types of gas pressure feed system. Okay, one is a regulated mode and the second one is blow mode. Okay, these are the two methods of gas pressurization in propellant feed system. Coming to the first one, regulated mode of propellant system. Here you can see this is the fuel tank and this is the oxidizer tank, and you can see combustion chamber. This is the combustion chamber. Okay, and this portion is your nozzle. Okay, and here you will have injector, right? The fuel has to be supplied from fuel tank to the combustion chamber like this. Okay, but we already discussed, right? We have to maintain some pressure P1 for the fuel and pressure P2 for the oxidizer. Okay, so how do you maintain this pressure? With the help of this high pressure gas chamber. We'll have one more chamber with which is filled with high pressure gas. Okay, this chamber is filled with high pressure gas, and in between this high pressure gas chamber is connected to the fuel tank and also connected to the oxidizer tank. Okay, so and in between we'll have a pressure regulator. Okay, you can see here you have pressure regulator which is located between the high pressure tank and the fuel and oxidizer tanks. Okay, with the help of this pressure regulator, we can control the pressure to be applied in the fuel and the pressure to be applied in the oxidizer, so that the required pressure will be maintained with the help of this high pressure gas. Okay, so when you control the pressure with this help of regulator, the pressures will be applied in the fuel and oxidizer, and whatever the fuel goes from the tank will also be maintained at the same pressure, which is developed, which is controlled with the help of this pressure regulator. So this is nothing but called regulated mode of feed system. Regulated mode of pressure feed system. We can regulate the pressure. We can regulate the pressure with the help of high pressure gas chamber. So this is about the working of regulated pressure mode pumping system. Coming to the next one, blow down mode. Okay, the second method in gas pressure feed system is blow down mode. The construction will be same, but this high pressure gas chamber will not be present in the blow down mode. Okay, then how we develop the pressure in the blow down mode? Simply what we do is we do not fill the fuel completely in the tank. Okay, here even you can see oxidizer also, only some portion, some empty portion is left. Some empty portion is left in the oxidizer tank. Here you can see the empty portion in the fuel tank and oxidizer tank. Okay, this empty portion is filled with pressurized gas. This empty place is filled with high pressure gas. Okay, which is actually inert gas. Generally we prefer inert gases so that they do not react with the fuel and oxidizer for any chemical reactions. Okay, so we fill this gap with high pressure gases. Whatever the pressure required, we fill with required pressure. If you want to maintain a pressure P1 in the fuel tank, we have to fill the pressure gas with pressure P1. If you want to maintain a pressure P2 in the oxidizer tank, you can fill the gas with the pressure P2. And we cannot control this pressure. Once we fill the gas in the fuel tank, that cannot be controlled. Once it is filled, that's it. Okay, so that is one disadvantage in this blow down mode. Okay, and next, the fuel is being supplied and oxidizer is being supplied into the combustion chamber. Okay, as the fuel and oxidizer is being supplied, the level of fuel decreases with respect to the time. The level of oxidizer is also decreases with respect to time in the tanks. Okay, then what happens? This empty volume, okay, this empty volume is the initial, the empty space is this much only, but after some time the empty space will be increases. The empty space will be increases even in the fuel and oxidizer tank. So what happens? Whatever the pressurized gas present in this propellant tank or oxidizer tank, that will occupy the volume of this pressurized gas in the tank will increases. So the pressure in the chamber in the propellant tank will be reduces as the fuel and oxidizer are supplied to the combustion chamber due to the increase in empty value. As the volume increases, the gases in the pressurized gases expands and the pressure in the propellant tank decreases. So the pressure at which the propellant and the pressure at which the oxidizer supplied to the chamber is also decreases gradually as the consumption of fuel and oxidizer. So this is one of the major disadvantage of blow down mode. But the complexity of this blowdown is less when compared to the regulated mode, and the design is very simple for blowdown mode. When compared to the blowdown, the regulated mode is somewhat complex, little bit complex, not that much compared to the blowdown mode. And the major advantage of this regulated mode is here well, we have high pressure gas, right? So we can maintain a constant pressure. We can send the propellant and oxidizer at a constant pressure to the combustion chamber. So these are the differences. Okay, coming to the regulated mode and blowdown, and the working of regulated mode and blowdown pressure feed systems in liquid propellant rockets. Okay, there are several sources of pressuring the gases. Okay, tank pressurization systems are there. There are different methods of pressurizing the tank. Coming to the high pressure inert gas, we can use high pressure inert gases, and even sometimes we can maintain a heated high pressure inert gases. We can heat the inert gases and send it to the propellant tanks, and sometimes during in a monopropellant or sometimes the reaction, the propellant get reacted, chemical reaction happens and pressure develops automatically in the propellant tank, and evaporated flow of small portion of cryogenic liquid. If the propellant is cryogenic, okay, if the propellant is cryogenic, generally what happens is the cryogenic propellant has to be stored at low temperature very low temperature. Okay, if you are not able to maintain, or if you increase the temperature of the propellant in the cryogenic propellants, automatically they will start expanding. Okay, they will turn into vapor state. So evaporated flow of small portion of cryogenic liquid, that will also be develop pressure in the propellant tank, that will also leads to the pressure development in the tanks. Even sometimes we have to maintain a venting system to avoid excess pressurization of the propellant tanks in cryogenic propulsion system. And okay, that is nothing but a self pressurization of cryogenic propellant, and direct injection with the help of pumps. Direct injection of the propellant with the help of turbopump, and we can maintain the required pressure. These are all the different methods that we can maintain for gas for pressure feed systems. Okay, and here we can go through the differences. Okay, differences between the regulated mode and blow down mode. Okay, coming to the pressure and thrust. Okay, the pressure stays essentially constant. The pressure and thrust essentially constant, because in the regulated mode we maintain the constant pressure with the help of pressure regulator. Coming to the blow down, the pressure decreases as the propellant is consumed. Okay, and next gas storage. Okay, gas storage, a separate high pressure tank to be maintained in regulated mode, and there is no need of any separate tank. Gas is stored inside the propellant at a tank pressure with a large ullage volume. Okay, and the propellant cannot be filled completely in the blow down system. Okay, this is the disadvantage. And required, okay, you needs regulator. We need regulator for regulated pressure mode of system, and filters. We need gas valves. Okay, and gas tanks also required. Coming to the blow down mode, larger, heavier propellant tanks are required compared to the regulated mode. In the regulated mode, the propellant tanks size decreases because there is no need to maintain empty space here. But coming to the blow down mode, we have to maintain some empty space. The size of the tanks will be increased. Larger, heavier propellant tanks will be used in blow down mode. Coming to the advantages, nearly constant pressure feed gives essentially constant propellant flow and approximately constant thrust specific impulse. Okay, and constant burning rate. We can maintain the required propellant thrust. We can maintain constant propellant thrust in regulated pressure mode. Okay, coming to the blowdown mode, it is a very simpler system, so less gas required, can be less and inert mass. The gas required, no need of pressurization tank. Okay, the mass of the blowdown system is less. Okay, these are, and the complexity of the system is less. So these are the advantages of blowdown mode. And coming to the one more advantage for the regulated mode is better control of mixture ratio. We can maintain the proper mixture ratio of fuel and oxidizer with the help of pressure regulator. Okay, coming to this blowdown, no high pressure gas tank. There is no high pressure gas tank, so it is difficult. Okay, next, slightly more complex, right? And regulator introduce a small pressure drop. Whatever the pressure regulator you maintain, that will leads to a small pressure drop in the regulated mode. So what we do is we have to correct that error while setting the pressure regulator. I have to calculate that error, which how much error is there, how much pressure drop is going to be maintained with the pressure regulator, and we have to increase a little bit based upon our requirement. And here the disadvantage, thrust decreases with burn duration, and high residual propellant due to less accurate mixture ratio and control. Coming to the blowdown, the pressure decreases in the tank, the propellant supply will not be 100%. Okay, at the end, the pressure in the tank will be completely less. Okay, when compared to the initial. So the complete propellant cannot be consumed, and there will be some residual propellant due to the less accurate mixture ratio control. The mixture ratio also cannot be controlled well in the blowdown because of there is no regulation in the pressure. Next, gases stored under high pressure often for a long time. So we have to maintain a high pressure gas chamber for a long time. This is one more disadvantage. Coming to here, the thrust must operate and stable over wide ranges of thrust values and modest range mixture ratios. It is difficult to maintain a constant thrust. So we have to control continuously, okay, in the blowdown, and it requires more pressurized gas. Coming to here, the propellant stored under pressure slightly lower specific impulse toward end burning time. Whatever the specific impulse will not be same in the blowdown mode as at the starting, okay, starting of the propulsion system. So coming, these are all the differences between the regulated mode and blowdown mode. Pressure and thrust, gas storage, required components, advantages and disadvantages. So this is about the gas pressure feed system. So accurate, if you want to maintain an accurate and constant thrust profile, we should go for regulated pressure mode. Okay, the constant thrust is not that much like a requirement. Okay, priority is not that much priority. Then we can go for blowdown, and we can reduce the mass of the propellants, like mass of the propulsion system. So this is about gas pressure feed system, regulated pressure mode and blowdown pressure pumping system. And here you can see the schematic diagram of the pumping, okay, pressure feed system. Here you can see the vents, okay, and even we have one gauge here, separate gauge for the fuel tank and separate gauge for the oxidizer tank, and so that we can monitor the pressure in the propellant tanks. Okay, pressurized gas is stored inside the propellant tank, right? So this is the empty space, and whatever the pressure in the tank, that can be observed with the help of these gauges 1 and 2. And here this is a fuel and oxidizer. Only 2/3 is filled because we have to store high pressure gas in this tank. And okay, fill and drain valve, or if we can fill the propellant tank and drain with this help of drain valves. And this valve is to control the flow rate. This valve is to control the flow rate, and filters any contamination in the stored propellants, that will be filtered with the help of these filters, and whatever the filtered propellant will be supplied in the required proportion, and these are the fuel injectors. Okay, these fuel injectors will inject the propellant in a atom like a vapor. Okay, this will atomize the liquid propellant into vapor, and the vapor will mix it in the combustion chamber and burns and thrust produces. So this is about the gas pressure feed system. Okay. Next, liquid propellants and their properties. Okay. Coming to the types of liquid propellants, we can classify into two types, in two different ways we can classify. One is based upon the types of propellant, like whether it is fuel and oxidizer, mixed bipropellants, monopropellant, hybrid propellants, like that. Another classification is based upon the energy content in the chemical substances. Based on that, we can classify the liquid propellants. If you classify based upon the energy, there will be like a low energy propellants, medium energy propellants, and high energy propellants. And if you go with propellant storage, okay, okay, then this can be classified into three types. One is monopropellant, bipropellant, and hybrid propellants. Okay, monopropellant means a single chemical substance contain both oxidizer substance and fuel atoms and oxidizer atoms, so that it is a single substance. Okay, then that type of propellants are called monopropellant. Bipropellants means separate fuel and separate oxidizer will be there. Coming to the hybrid propellants, fuel will be in separate physical state and oxidizer will be in another physical state. For example, in bipropellants, if the fuel is in liquid state, the oxidizer will be also in liquid state. But coming to the hybrid propellants, if the fuel is in solid state, the oxidizer can be in liquid state. Okay, or they will be in different state. One will be in liquid state, another will be in solid state, or one will be in liquid and another will be in gaseous state, like that. Hybrid propellants. Okay, combinations based upon the propellant combination. Coming to the monopropellants. What is monopropellant? Monopropellants are liquids which may be stored in a single tank. So monopropellant means a single substance contain both oxidizer and fuel atoms. So we can store this only one propellant tank is required if you use monopropellants. If you use monopropellants, only one propellant tank is required. They are decomposed, releasing energy in presence of catalyst. Okay, this monopropellant decompose. Generally, we have to start reaction. If it reacts, then only energy will be released, right? So in order to start for a reaction, we use catalyst. We use catalyst for decomposition of this monopropellant. Examples are hydrogen peroxide. Okay, here we have H2 and O2. Okay, both one is fuel atom, one is oxidizer atom. They will react and produce the energy. And next, hydrogen N2 and H4. This will also consider as a monopropellant. Coming to the hydrogen peroxide first. Okay, it was used as a propellant for the first and the second stage of Soyuz launch. Okay, in the Soyuz, we have used this. It is all hydrogen peroxide is used in the first and second stages, and also used in the Mercury manned spacecraft. Also, this hydrogen peroxide as a monopropellant. The propellant slowly decomposes by itself. Automatically, it will decompose, so it cannot be held for years, and thus cannot be used in spacecraft for long time. So the disadvantage, coming to disadvantage, is it decomposes slowly automatically. So we cannot store a monopropellant for a long time. Whenever the mission is going to start, before that we have to fill the monopropellant in the propellant tank. Okay, and the we cannot store for long duration, so it cannot be applied for spacecrafts. Why? Because the spacecraft lifetime will be very high when compared to the normal missions like missile operations. Are okay, so we cannot use these monopropellants for spacecrafts because of long lifetimes. And coming to the next propellant, hydrogen, monopropellant hydrogen, it was used in the thrusters of Voyager spacecraft, in the descent engines of the Viking and the Phoenix, okay, Martian landing probes, etc. It is used for space applications. It is used in the spacecraft. Okay, Voyager spacecraft, Viking, Phoenix, and Martian landing probes also. The hydrogen is the monopropellant used for this. Okay, it is stable when compared to the hydrogen peroxide. Okay, it is stable, and we can store this for long years, for long duration. So we can store hydrogen for long duration. Coming to the advantages, what are the advantages of monopropellant? So they need only one tank. The structural, so if we need two tanks, the structural weight we have the second tank weight will be reduced here. So only one tank is required, and the ignition system is not needed. Self decomposition, or we can use catalyst for reaction. So separate ignition system is not required. Next, they may work for a longer time. Okay, depends upon the property of monopropellant. We can it will work for long time. Okay, and restarted several times for short duration. So we can restart the engine for several times. Even we can run the engine for a short duration, and we can shut off with the help of this monopropellants. So these are the advantages of monopropellant. Coming to the disadvantages, the low specific impulse. Low specific impulse is the disadvantage for monopropellant. Okay, the next one is bipropellant. The next one is bipropellant. Coming to the bipropellants, these propellants consist of fuel and oxidizer that should be held separately. So separate fuel. Fuel will be a separate substance. Oxidizer will be a separate substance. So we have to store separately. Okay, when they react in the thrust chamber, when it is ignited. So the fuel and oxidizer react each other when we start ignition. Okay, these type of propellants are called bipropellants. Fuel will be as a separate substance, oxidizer is a separate substance. Oxidizer plus fuel will become a propellant. That propellant are called bipropellants. Okay, so here we have to store propellants in two tanks. So definitely two propellant tanks are required here. So propellant bipropellant mixtures divide in practice by their properties into hypergolic and cryogenic propellants. These bipropellants again divide into two types, hypergolic and cryogenic propellant. Hypergolic propellants means these are react spontaneously. These propellants react when spontaneously when contact when we make this fuel and oxidizer contact each other. Coming to the cryogenic propellant, these propellants have very high specific impulse, but we have to store these propellants at a very low temperatures. Okay, and that is about the cryogenic propellant. Okay, coming to the fuels, coming to the fuels, coming to the bipropellants, the fuels are general fuels are kerosene is one of the fuel, hydrogen, monomethyl hydrogen, and hydrogen. These are the basic fuels which we used as a in a bipropellant. And coming to the oxidizers, oxygen. Anyway, oxygen is a separate substance, so it can be used as a bipropellant in the bipropellant. N2O4 and HNO3. Okay, these are the general oxidizers and fuels which we use for bipropellants. Next, hypergolic. In that, hypergolic propellants, right? We have bipropellants are divided into two types, right? Hypergolic and cryogenic, right? Hypergolic propellants. Hypergolic mixtures ignite spontaneously when brought in contact each other. When you make fuel and oxidizer in contact each other, automatically the reaction starts. Then that type of propellants are called hypergolic propellants. Okay, some propellants cannot react. Even though you mix fuel and oxidizer, does not react. You have to provide separate ignition system. Okay, those are different. But hypergolic propellants automatically start reacting each other when in contact, brought in contact. Okay, this eliminates complex ignition system and starting. So this hypergolic propellants helps us avoiding ignition system and starting. Okay, propellant combustion starting mechanisms. Okay, the process of combustion is more stable. Okay, so engines are more simple to develop and less likely to be destroyed at work. Okay, the complexity of there is no need of ignition system, right? So the complexity of design is reducing when we use hypergolic propellants. So what we observed here is based upon the propellant type, the design of the engine will varies. Okay, the engine has to be designed based upon the propellants to be used. Okay, hard spats are less likely when compared to the with the hypergolic propellants. Starting is very easy in hypergolic propellant. So the most widely used hypergolic mixture is hydrogen or its variants. The hypergolic propellants are hydrogen and its variants are comes under hypergolic propellants. Okay, fuels. Coming to the fuels, right? Monomethyl hydrogen, hydrogen variants, right? So monomethyl hydrogen, UDMH, unsymmetrical dimethyl hydrogen, okay, aerosine, 50% of hydrogen and 50% of UDMH. The mixture is called aerosine. Okay, so these are the fuels of comes under hypergolic propellants. And coming to the oxidizer, dinitrogen tetroxide N2O4. Okay, N2O4 is a one type of oxidizer comes under hypergolic propellant, and nitric oxide NO is also comes under hypergolic propellant. Okay, next category of bipropellant is cryogenic propellants. The cryogenic propellant already discussed, right? The cryogenic propellants are liquefied gases. These are liquefied gases which are lower than the ambient temperature, such as if you say liquid oxygen, it is stored at minus 183 degrees centigrade. Okay. Generally, oxygen at normal STP conditions will be in gaseous state only. But when you bring this oxygen to a temperature of minus 183 degrees centigrade, then this oxygen will turn to liquid, which is called as liquid oxygen. So this liquid oxygen at minus 183 degrees centigrade or below it is considered as cryogenic propellant. Okay, so whatever the gases, liquefied gases are considered as cryogenic propellant. And another example, liquid hydrogen. Liquid hydrogen is also in a gas. Generally, hydrogen is also in gaseous state at STP conditions, but at minus 253 degrees centigrade, the hydrogen will turn to liquid. So this is also used as a liquid cryogenic propellant. Normal hydrogen at STP condition is not a cryogenic propellant. Liquid hydrogen is only considered as cryogenic propellant. Okay, we should not get confused here. Okay, the provisions for venting the storage tank and minimizing the vaporization losses are necessary to be maintained in cryogenic propellants, because the propellants are stored at very low temperatures, so thermal insulation should be very perfect. Okay, thermal insulation should be perfect, otherwise there will be some heat transfer and the propellant temperature will rises and vaporization chances are there. So we have to minimization of vaporization loss is a major task in cryogenic propellant, and we have to even provide some venting for the storage propellant storage tank, because the pressure self pressurization happens in the cryogenic propellants, and the pressure should not increase beyond the strength of the propellant tank. If the pressure increases beyond the strength of the propellant tank, the propellant tank will fail and it will lead to a big explosion. So we have to take care of these things in the cryogenic propellants. And coming to the properties of liquid propellants are categorized as their specific impulse. Okay, coming to the specific impulse, they are categorized into three types: low energy propellants, medium energy propellant, and high energy propellant. Okay, low energy propellants. Coming to the low energy propellants, whatever the propellant that can produce a specific impulse at sea level which is less than 3000 Newton second per kg. If the specific impulse is less than 3000 Newton second per kg, then that particular type of propellants are called low energy propellants. Okay, so here you can go through the examples of low energy propellant. Liquid oxygen, LO2, and alcohol. It is a mixture. Okay, it is considered as low energy propellant. It will produce a specific impulse less than 3000 Newton second per kg. And next, liquid oxygen with kerosene. Okay, which is also called as rocket propellant. It is also comes under low energy propellant. And nitric acid with aniline, nitric acid with xylidine, and nitric acid with hydrogen. All these combinations are also considered low energy propellants. Okay, next N2O4 with hydrogen and monomethyl hydrogen and unsymmetrical dimethyl hydrogen. The combination of N2O4 with hydrogen, monomethyl hydrogen and unsymmetrical hydrogen, all these combinations are also comes under low energy propellants, which will produce specific impulse less than 3000 Newton second per kg. Okay, next medium energy propellants. Medium energy propellants. The specific impulse we here, the propellants which having specific impulse in between 3000 to 3500 Newton second per kg, then that particular propellants are called as medium energy propellants. Medium energy propellants. Coming to the list of medium energy propellants, UDMH, okay, N2H4, AZ50, Aerosine, LO2, okay, and kerosene with liquid fluorine, okay, kerosene with liquid fluorine, UDMH N2H4 and AZ with AZ50 with LO2, liquid oxygen, kerosene with liquid fluorine. All these are comes under medium energy propellants, but in most cases these medium energy propellants are not much used in a practical applications. Okay, the medium energy propellants are not popular, and only UDMH with LO2 combination has been used in practice compared to the other propellants. So the use of, coming to the use of fluorine, it is difficult in view of its toxicity and reactivity. Fluorine is generally a toxic substance. Okay, because of that we try to avoid fluorine in as maximum as possible for any application. Okay, so the medium energy propellants are not that much popular, but only UDMH with a liquid oxygen combination is only is there in some practices, used in some practices. Coming to the next, high energy propellants. Okay, high energy propellants are nothing but the specific impulse should be greater than 4000 Newton second per kg. Okay, if it is less than 3000, it is low energy propellant. Between 3000 to 3500 or 4000, then it is medium energy. More than, greater than 4000 Newton second per kg, then that propellants are considered high energy propellants. Coming to the examples, liquid hydrogen with liquid oxygen. This combination will become a high energy propellant, and liquid hydrogen with liquid fluorine. This is also one combination of, which leads to the, which act as a high energy propellant. Okay, so liquid hydrogen, liquid oxygen means cryogenic propellant, and liquid hydrogen and liquid fluorine, this combination is also a cryogenic propellant. So cryogenic propellants comes under high energy propellants. The only high energy propellant used in practice is liquid hydrogen and liquid oxygen as a cryogenic. We already discussed, right? Liquid fluorine, which is a toxic substance, okay, which is a toxic one. That's why we always try to avoid usage of liquid fluorine. So liquid hydrogen and liquid oxygen combination is mostly used as a cryogenic propellant. So this is about high energy propellants, right? Coming to the summary or summary of today's lecture, we have gone through the introduction of liquid propellant rockets. What is liquid propellant rocket and what are the components in liquid propulsion system? After that, we have gone through the types, liquid propellant feed system. What is liquid propellant feed system? The importance of liquid propellant feed system in the liquid propulsion system. And we have gone through the types of liquid propellant system. And next, in that we have discussed about the gas pressure feed system. In that we have discussed two types. One is regulated mode and blow down mode. After that, we have gone through the properties of liquid propellant, and in that that is liquid oxidizers and liquid fuels. Okay, this is so this is about the summary of today's lecture, and we'll meet in the next lecture. Thank you.